Okay, Keith gives me the go-ahead. So we're going to be doing a lot with finite fields over not just FP, but extensions of FP. So we need to know a little bit about constructing them and various operations on them, how to work with them. So I'm going to briefly discuss the constructions. So let F be a degree n polynomial over Fp. We want it to be irreducible, so that means we want it not to factor into a product of lower degree polynomials. Okay, and I'm going to say alpha is a root of f. The formal construction, of course, of this is Kroneker's theorem, by which I mean you take a polynomial ring over Fp, you take the quotient by the ideal generated by f, and this equivalence class in your quotient is basically alpha. And so that gives you something to work with. But it's a pain to write out x plus f, the ideal generated by f all the time, so it's easier to just use alpha. And it's a field, so of course we're allowed to take quotients, but you have inverses, so you can easily get things in the form a0 plus a1 alpha up to an minus 1 alpha to the n minus 1 a sub I in Fp, where the powers in alpha are a basis over Fp as a vector space. And you can see this because if you had them being linearly dependent, then you would have a polynomial of lower degree satisfied by alpha. And so then f itself would not be irreducible because that polynomial would be a factor of f. So that gives you the fact that it's a basis. And so that already tells you the structure of the additive group of this field. You know that it is basically a bunch of, it's a vector space. It's just like, so the additive structure is isomorphic to n copies of z mod pz, of course, just from the vector space structure. And it takes a little bit more work to show that the multiplicative group is cyclic. I'm not going to go through that. You can look at my notes for that, but it's true. And I'm going to do a quick example, easy example, the example everyone should know. All right, so if I want to construct a field with 4 elements, I am working over F2, and I need a quadratic irreducible polynomial. There is only one. for any quadratic polynomial to be reducible over some field, you are basically looking about whether or not it has a root in that field, because if it factors, both factors are going to be linear. And the same goes for a cubic. If you can show that a cubic is irreducible if and only if it doesn't have a root in your ground field, because it would have at least a linear factor and a quadratic factor. Maybe it would split into 3 linear factors, but you're at least guaranteed 1 linear factor if it's going to factor at all. Above that, then you're having to play more games to show irreducibility. In the case of F2, to show that something's that doesn't have 0 or 1, you're just plugging in. And you can do the plug in for any FP, but checking 0 and 1 is easy in any field. To see if 0 is a root, you're looking only at the constant term. To see whether 1 is a root, you're looking at the sum of the terms. The sum of the terms has to be 0 in whatever the field is. So over FP, we're saying simply that the sum of the coefficients is even for it to be have 1 as a root. So you simply need a polynomial that's quadratic, has 1 as the constant term, and an odd number of non-zero terms total. Well, there is only one of those, and that is this. And so that gives you your irreducible polynomial over F2. And so if you want to do your computations with this, you get this equation, which implies this equation because we're over F2 and minus signs don't matter. And so if you want to do, say, alpha plus 1 times alpha, you get alpha squared plus alpha equals alpha plus 1 plus alpha equals 1. So they are inverses of each other. And in fact, this is the other root of this polynomial. It really has to be, because this polynomial doesn't have roots in F2. It's separable. It has distinct roots, and there's only 2 other roots available to it. So, but you can also do the computations to show that it's that alpha is a root. So I don't want to spend any more time on that detail. Hopefully it's clear. But I now want to discuss Frobenius. Are there any questions on that before I discuss Frobenius? So now I'm going to denote Frobenius by sigma from Fp to the n to Fp to the n. And it's defined by sending x to xp. And the significance of this, so this is a homomorphism, and that's not something you would expect if you were working in characteristic 0, because, of course, it's generally not true that a plus b to the p is equal to a to the p plus b to the p, usually. Right? But we're in characteristic p, and if you were to actually apply the binomial expansion theorem to this, then all of the coefficients in between have p as a factor, which you can easily check by counting factors of factorials. And so they vanish, mod p. And so that means this is basically a well-defined homomorphism. It's actually an automorphism of the field. It generates the Galois group. Galois group is cyclic, so forth. All of that's discussed in my typed notes. So, but in particular, powers of this are also automorphisms. If you look at the case where k is equal to n, equal to the degree of the field, it's going to act trivially on it. And that's a very important point from theory of elliptic curves. We use it multiple times. Special case, n equals 1, you basically have Fermat's little theorem. That is that's the point here, because if you have i.e. x to pn minus x equals 0 for all x in FPGM. Right. So you see in the case where n is 1, that's basically Fermat's little theorem. So now we want to consider what happens when we apply this to curves, to points on curves, and how things work there. So the important thing to remember about automorphisms is that in the first place, being an automorphism means that it commutes with both addition and multiplication. Right? It has to be a homomorphism of the field in the first place. And over the field of definition, where it acts trivially, then it also it's important to understand that since if you're looking at sigma n, it's acting trivially on FPDN. If you have a polynomial with coefficients FPDN, it's going to act trivially on the coefficients. So if you have a curve, so if C is a plane curve, you can do this for more than just plane curves, but I mean, all of my examples are plane curves, so. I'm just doing it for plane curves because I want to get away with writing down one equation. All right, so if we have it given by this, where f is a polynomial whose coefficients are an FPDN, then sigma d n is going to act trivially on those coefficients. And so if I take f sigma n x, sigma to n y, I can pull out sigma to n because it is, well, sort of thinking of it backwards. So think about it going this way. So if I apply sigma n to this polynomial, it acts. It first can be distributed to each term individually. It can be distributed to each product individually. It then acts trivially on the coefficients, and then can be brought inside the powers by the fact that it works on the products, and so we get this, right? So I'm writing it backwards, but I'm writing it this way because now, if I have a point on the curve, then this is 0, right? So if sigma n applied to 0, and of course it's going to send 0 to 0. So the upshot is that sigma n sends a point on the curve to another point on the curve. So therefore, if P equals xy is a point on C, then so is sigma to the n dot P equals sigma to n applied to x and y. Running out of room there. Right, you get the point. So that is very important for what we will do. In particular, in the case of elliptic curves, it means that we actually have something that is well defined on what we call torsion. So we're going to discuss torsion now. Okay, so let O be the identity on the curve E. If P on E is a point such that NP, meaning repeated addition of P by itself n times, is equal to the identity, then P is called an N torsion point. Or it's said to be in the N torsion. There's several different ways we say this, okay? And you've seen a special case of this already. We did this in the case where N is equal to, well, we didn't discuss torsion, but we saw doubling, right? And so we were dealing with the case of repeated addition by 2 already. Okay, but it's important to understand that this does not mean that the point has order n, of course, because n may not be the least. So the least such n is called the order of P. I mean, that's just the usual definition, is the order P. The n torsion points are the points of order dividing n. That's important. But also, we know that no matter how many times we add the identity to itself, we always get the identity back. So the identity is always an n torsion point, and so we call it the trivial n torsion point, since n O equals O for all n, we call O the trivial n torsion point. So we have to be a little bit careful often when speaking of torsion points by saying that we have a non-trivial torsion point. If we don't have such a point, then we often say that we have trivial torsion, right? And, if we are over an algebraically closed field, we're going to have torsion other than trivial torsion. So this is only the question of whether we have trivial torsion is something that only comes up over small fields where we might not get everything, like over Q or over FP, not algebraically closed fields. So that's important. So let's look at some special cases. Interpretation for n equals 2 and 3. So for arbitrary n, of course, it would be tough to come up with a geometric interpretation. But there's a very nice geometric interpretation of torsion for n equals 2 and 3. 2 torsion is corresponding to basically points that have vertical tangent lines. Okay, they are if you have something in Weierstrass form anyway, right. So I mean, especially class y squared equals a cubit, vertical tangent line, and you get so you get that the y coordinate is 0. So you're basically looking at the root. Your x coordinates are the roots of the cubic polynomial f. So that's in the case of 2. So for y squared equals x cubed plus ax squared plus bx plus c, the 2 torsion points have vertical tangents. And then for 3, you have basically an inflection point, a line intersecting triply with the curve. And that can be stated generally without this polynomial here. So, I mean, technically, if you have something with general A's, yeah, you can still get it from in a similar way. I'm not sure vertical is really the best way to say it, but it's very easy, very nice interpretation with the 2 torsion. So for 3 torsion, inflection points. And so I already discussed in the last lecture that the point at infinity is a triple point on the curve, that the line at infinity intersects it triply there. It's an inflection point. And so that it should make sense then. I mean, it definitely makes sense from this perspective that from the perspective of repeated addition of the identity, that you're always going to get the identity, so it has to be a 3 torsion point. But it meshes well with this interpretation for 3 torsion, that it's a 3, that it's an inflection point. And in the exercises, I have a problem where I ask you to compute what's called the division polynomial. Division polynomials give you x coordinates of torsion points, and I ask you to compute it using implicit differentiation. So if you do implicit differentiation twice, you can figure out what the inflection points are, and that tells you then what your 3 torsion points are. For general division polynomials, they get pretty hard. I have the general formulas in the notes. I'm not sure. I don't think I have time to show them to you, but you can look in the notes. One look at them will convince you it's better left to a computer. at least if it's bigger than 4. All right, up to 4. Sure, you can do it by hand maybe, but I would not touch them for 5 torsion or higher by hand. That is but 3 torsion is totally reasonable to do by hand. I recommend it if you want to try that exercise, computing it with implicit differentiation. Okay, so we want to see what happens when we apply Frobenius to the torsion. And so if we have, action of Frobenius on torsion. Let E be an elliptic curve over Fp to the k. Then sigma to the k well, not only is our curve defined by polynomials over this field, so are the addition formulas, right? Because we're getting addition formulas basically by this algebraic computation, which happens completely over this field. And so this commutes with the addition. This is addition on the elliptic curve. So, I mean, there's something a little bit non-trivial going on here because while it's basically from the definition of endomorphisms that this commutes with ordinary addition, the fact that it commutes with this addition is coming from the definition of addition law on the curve. So, but it's true. It commutes with it. Okay, and so now, if P and Q are specifically end torsion points, well, I mean, so we can repeat this, right? We can repeat this by induction. So P sigma to the K. I think it's probably already clear where I'm going with this, but I'm going to write it down. All right, if we get it commuting with addition, we get it commuting with repeated addition. And so if NP is a torsion point, an end torsion point, then sigma k is going to act trivially on the identity. Why does it act trivially on the identity? Well, remember, for the identity we had this. That's defined over the base field Fp. So it's going to act trivially on that. And so basically what we get is n sigma k dot p equals sigma k and p equals sigma k o equals o. So sigma k is well defined on n torsion. And if you look specifically at prime values of n different from p, so we often call those primes L, just distinguishing from p, we have a vector space in terms of repeated addition of the points with a different structure, not over Fp over Fl. So we'll be dealing with that probably not so much today, but tomorrow it's going to come up quite a bit. And we'll be able to get matrices. Yes?
So yesterday we had been talking about algebraically closed fields, elliptic curves over algebraically closed fields.
Yeah.
How is this affected by not being algebraically closed as in this case?
Well, how's it? So the question was, how is this affected by not being algebraically closed? Like if you're starting with a point that is in Fp to the k or some extension, but not over the algebraic closure, how does that affect this? Well, it affects what you have as two torsion points available to you. Okay, but if you have a certain torsion point available, then the action of Frobenius on this is exactly like this. All right. It could be that you only have trivial torsion. And so then the action of Frobenius is quite boring. It's just, acting on O, sending to O. That's it. But so when we discuss the vector space structure tomorrow, we are going, the chore is to extend to a field that has full torsion. And so that's the real trick, is figuring out where the full torsion is. And so the division polynomials are useful for that, figuring out how to find the torsion. But again, not something I would want to do by hand. So when we do it tomorrow, I will be writing down the Sage code that can do that for you. So I hope that answered the question. So now let's look at a simple example. And this is an example I like a lot for many things, except it is not well suited to what I want to do tomorrow. Okay, so this is an elliptic curve that is not defined over F2, but it is defined over Fp when P is odd. And there's a condition that tells us whether or not we have full 2 torsion or not, just based on congruences. So x squared plus 1 factors over Fp if minus 1 is a quadratic residue. And so therefore, if P is congruent to 1 mod 4. And it does not if it's non-residue. Okay, and if it's in the case of P equals 0, then this is not even an elliptic curve. It's singular. So, so for an interesting example here, what we want is a prime congruent to 3 mod 4, because if I pick something where I have full torsion over Fp, well, Frobenius is going to be acting trivially on it. It's not going to show you anything. It's just going to send each of the 2 torsion points to themselves. We want something a little bit more interesting than that. So I'm going to take P equals 3. So then x squared plus 1 does not factor. It's irreducible over F3. So you can use it to construct an extension that has a root, right? So let alpha squared plus 1 equals 0. That gives a very nice simple x-coordinate to use for our 2 torsion point. So, and we know that the y-coordinate is 0. So that means that we have, so our 2 torsion is 0, 0, alpha 0, minus alpha 0, and the identity. And so we want to look at the action of Frobenius. Well, Frobenius acts trivially on that one, clearly. If you cube 0, you get 0. Phi of alpha 0 equals alpha cubed 0. Equals alpha squared times alpha equals minus alpha. So what phi does is it exchanges these two, these two torsion points and fixes this one. Now, if we wanted to get a matrix, we would have to set up a basis for the two torsion. We won't do that with this example. We'll do it with the ones I'm using on Wednesday. But for two torsion, basically any pair of these points could be picked as a basis. And so you get different matrices. The matrix that you get is not going to be unique, of course. And I should also say that when you look at the action of Frobenius, well, I'll save that discussion for Wednesday. But I mean, it's only giving you the action. The matrix you get from this construction is only giving you the action on the L torsion, whatever L is. In this case, L is equal to 2. So this is action of phi on L torsion for L equals 2. And that's important. It does not give you the full action for Frobenius, but it gives you a piece of the picture. Okay, so we now need to discuss the concept of an endomorphism. All of these things we've been discussing so far are examples of endomorphisms. Phi is called an endomorphism. Let me use psi. Psi is called an endomorphism of E. If it is a homomorphism I mean, there's better definitions that don't require as, I mean, this is a bit heavy-handed. You can use weaker definitions to define it, but I'm trying to avoid going over a whole lot of algebraic geometry here. So the deal is that, of course, it does not have to be surjective. It doesn't have to be an automorphism. You can send everything to 0, for instance. I say 0. I mean the identity, of course. So I would call the endomorphism we would denote by 0. So 0 dot p equals O for all p. Okay, that's one option. We have n dot p for n and z for positive integers. If we take n equals 1, we're just saying we have the identity. We're sending everything to itself. For n 2 or greater, we're looking at multiples. doubling, tripling, and so forth. And of course, we have negation, sending a point to its inverse. And so between these two together, we can also get all negative n, right? By composing those. By composing B and C, we get all in C. All right, all negative n. So basically, we have one endomorphism for every integer. And that's true regardless over what field we're working with. But over finite fields, we also have the Frobenius endomorphism. So over finite fields, f p to the n, phi sending okay, and there are cases even when you're not working in over finite field where you may get other endomorphisms. I don't really have an example of that in these notes because we're supposed to be talking mainly about finite fields, but I do have the general description of what I do have the general theorem, which we will do. But this is so, and there are also other options for finite fields sometimes. That's a very important point. So let me do the general theorem. But basically, I hope you're getting the idea of what's going on here. You can consider maps from the elliptic curve to itself, and these maps often provide useful information about the curve, and they're also useful tricks in cryptography in terms of speedups with, say, the Frobenius endomorphism. So, theorem. I'm not going to prove this at all. This theorem is discussed in Silverman's book on elliptic curves, so you can read it there. If E is an elliptic curve, then endomorphisms of E form a ring isomorphic to one of the following. Z, hopefully there's no surprise there. We have all the integers available to us as endomorphisms, so that's an option. We could have only those. And that does happen with elliptic curves over the rationals. Say. Then second option, in order in an imaginary quadratic number field. I'm not sure if you know what the general concept of an order is. It's not that important to us for our purposes. Here it's a subring of some kind. Certainly as examples of orders, you have the integers in the number field, but that's not the only option. Orders are sort of to be a little bit more general than the integers themselves. And 3, an order in a quaternion algebra. And this, so we'll discuss what each of these mean for curves over finite fields shortly, but let's continue with their names. So in case 1, E is often said to have trivial endomorphism ring. Case 1 is said to have trivial endomorphism ring. Case 2, E is said to have complex multiplication. In case 3, E is said, or the CM is used as an abbreviation often. E is said to be supersingular or superspecial. Supersingular is the historical definition. And, you know, I understand that, but it can be misleading. And so in my notes anyway, I try and stick with super special, I hope for clarity. But if you encounter most sources are going to use the phrase super singular. The point is, it's not. It doesn't have anything particular to do with what we consider as a singularity these days, and so that's why it's somewhat confusing. It looks like I'm nearly out of time. I'm going to. So let me first quickly say what the relevance is to curves over finite fields and number fields. So over number fields, the third one can't occur at all. Over finite fields, obviously we have the Frobenius endomorphism, always, right? And so the first one can't occur. But the third one can, and that is crucial for elliptic curve cryptography, because the super singular curves or super special curves are terribly unsafe. And so they need to be avoided. So we need absolutely a criteria to help us find them. And rather than having to write it all from scratch, I'm just going to put this up here. So is that in focus? It doesn't look like it's in focus. I don't know where the focus is. Look at my my notes, my PDF notes. So there's this theorem due mostly to Turing that gives a couple different criteria for testing whether something is super singular. And then I go through this little argument that's sort of sketchy and explain how in certain cases that are useful to us, it is equivalent to having trace 0. Trace AP is going to be, as we will learn, the trace of the Frobenius endomorphism. And so if you can compute that, which is computable in polynomial time using the algorithm I will show you tomorrow, then you can easily determine whether or not it is super singular or super special or not. And so that is one strategy. And there are other problems related to that in the exercise. Questions about any of what we did? We're basically out of time for today.